We present an optimization framework for simultaneous grasp and motion planning in the context of robotic assembly. Grasp and motion planning has been investigated since the dawn of robotics and is still one of the most active fields in robotic research. Despite the major progress in dexterous manipulation of objects over the last few years, there are still many hurdles left to overcome. While pick-and-place tasks are considered to be on the simpler side of manipulation problems, they become far less trivial in the context of assembly. Assembling a structure from parts, for example, building brick walls or sorting and stacking packages of different sizes and properties, is in general straightforward for humans. But for robots, even those relatively simple tasks become challenging. This particular issue lies in the fact that for assembly tasks, the environment is initially free of obstacles, but gradually becomes more constrained and motions become more restricted. This means that robots need to find strategies to avoid colliding with the structure they have already built. And this, indeed, to a large extent, involves how to grasp an object as much as it involves the motion itself. Our goal in this work is to create a framework that generates optimal grasp configurations and motions for robots simultaneously in order to solve assembly tasks in a smooth, efficient, and collision-free manner. Our setup employs commercially available manipulator robots with standard parallel grippers, which manipulate simple wooden blocks. The assembly itself is broken down into simple pick-and-place tasks. We propose a new approach to tackle this problem, and we demonstrate it in a variety of different scenarios. The input to our problem is a set of objects with known poses, their target poses, and timing information describing when objects need to be picked up and put down. Given this information, our framework jointly searches for the optimal grasp and the optimal motion to perform the task, which is then transferred to the robot for execution. We formulate this problem by using a model-based approach where the robot's configuration is defined by its joint angles and kinematics. The motion trajectory is discretized into a sequence of joint angles. The main objective is to pick a block from its initial pose and place it in its target pose, where the timing information for both pick and place is given. However, it is not predetermined where the gripper comes in contact with the block. This can be formulated as an optimization problem. In our formulation, we differentiate between three sets of parameters: the location where the robot grasps the block, the robot's joint angles for each pick and each place pose, and the joint angles for the trajectory in between. To allow robots to reason about the way in which grasping locations govern the optimal motions, we formulate the problem using a tri-level optimization scheme, where each of the optimization levels computes one of these parameters. The top layer finds optimal grasping locations within the boundaries of the block. The mid layer finds optimal robot poses for the pick and place configurations using inverse kinematics. And the bottom layer finds optimal collision-free motion trajectories that connect these IK configurations. We leverage sensitivity analysis to compute first and second total derivatives of the top layer, which allows us to employ an efficient numerical solver based on Newton's method. Solving this optimization scheme generates solutions that are optimal in terms of both the grasping location and the overall motion, meaning that solutions represent the optimal grasp or the optimal motion given a specific assembly task. For more details about this method, we would like to refer you to the paper. Now let's see some results. Our framework can be used to find optimal grasping locations within the object's boundaries to avoid obstacles. This is an interactive example where the user moves the obstacle towards the robot halfway through the trajectory. Note how the grasping location changes to avoid collisions during the motion. We can also leverage grasp optimization to get smoother motions for the assembly. In this pyramid example, we compare fixed with optimized grasping poses. By looking at the resulting motions, we can see that being able to choose a suitable grasp allows the framework to come up with motions that are more natural, direct, and efficient. Our framework also allows to simultaneously optimize for other hyperparameters. For example, for dual-arm robots, such hyperparameters can be the position and orientation of an object during handover. This allows the robot to hand over the object from one arm to the other wherever it is most convenient in terms of reachability, collision avoidance, and motion smoothness. The biggest advantage of the grasp optimization is that it allows us to build structures that would not be feasible otherwise, such as, for example, this triple truss. The first truss can be assembled without any concerns, but for the second and third one, a suitable grasp is crucial in order not to knock down the structure that has already been built. While our approach is rather flexible, we currently demonstrated it only for the simple longitudinal grasp space. The ultimate challenge would be to formulate a differentiable grasping model of arbitrary objects and apply it to our framework. Similarly, our model currently only supports parallel grippers. A follow-up work would be to generalize it to more dexterous grippers, such as robotic hands or soft grippers. In terms of assemblies, we only treated the grasp and motion optimization part. However, a significant part of the problem is the sequencing, which describes in which order and timing the object should be assembled. Sequencing in general has a more discrete nature to it, which makes it challenging to integrate into our differentiable formulation. This is definitely an interesting problem for future investigations. Thank you very much for your attention.